Right, so weight will come into play here is 15 pounds. Yeah. Right, so in this case, this is different than how the exam question 2 was set up. In this one, they do tell us that when it's horizontal, the spring is unstretched. You could not make that assumption in the exam problem. If you did, you got the incorrect answer. In the exam problem, it did not say that when the string was horizontal, the spring was unstretched. In fact, it was still stretched even when it was horizontal in the exam problem. But here it says something different, so we want to know that, in this case, the unstretched length is 3 feet. And what other information is given to us that might not be in the picture right away? Yeah. Right, so it's in equilibrium when that theta value is 30 degrees. In the diagram, it just calls it theta. Right, and what we're trying to find here is, for this to be the equilibrium position, what must that stiffness in the spring be? So what is K that makes this in equilibrium? So for our free body diagram, what is the object we want to isolate to be able to find, or do we think is going to work to find what we're interested in?
Rod AB.
Right, so rod AB, we're going to disconnect it from the spring, we're going to disconnect it from the pin at A. So it might not be necessarily intuitive that that's what we want, but if we kind of think ahead a little bit, we're going to need the spring stiffness. This comes out of Hooke's law. Hooke's law relates the force in the spring to the spring constant as deformation. Therefore, we're going to need to know the force in the spring. Therefore, we need to disconnect that spring from this rod in order to find out what that force is. So it's very possible, especially more complicated ones, that the first free body diagram you draw is not sufficient to answer the question. And we're going to see in Chapter 6 that you can't do it with a single free body diagram. You'll need multiple ones. So there's kind of an art to decide what object or objects do we want, and that'll come with experience of starting to do these problems. So right, AB is going to be the good object to choose for this. So take a couple minutes and at least sketch out most of the free body diagram. Some of it will be a little bit more complicated detail-wise. We'll get to that in a little bit. All right, so again, we're taking AB. So draw at least most of the free body diagram. All right, so here's kind of the skeleton of the problem. I just have my object. So the forces that are going to act on it. So we do have to include, in this case, the weights of the rod. So since it's uniform, it'll act at center, 15 pounds. We have that pin connection at A. So we'll have an AY and an AX. And at B, if we're disconnecting it from the spring, we'll have that force in the spring I'll call FK. Now, we kind of do have enough information in the picture already that is complete, but I want to find that angle beta. It's going to make the equilibrium equations easier to write in the next step if I just find explicitly what the value of beta is here. But again, that's going to point, we know the spring has to point from B towards the point I called C. So unknowns, we're going to have the force in the spring, AY and AX. So before we even get to the equilibrium steps, I want to go through and just find what that angle beta is, which is the same as this beta here. So there's different ways we could do this. I'm going to use law of cosines and law of sines. But if you do draw enough of the coordinates here and figure out where their locations are, you could do it without using law of sines, law of cosines. But this is what our triangle looks like here. We know that's 6 feet from A to C. We know it's 3 feet from A to B. And we know that this angle is 30. So we can find L naught using the law of cosines. We know the 3, the 6, and the opposite angle. So using law of cosines, this is L prime. L prime using law of cosines is going to give us 3.72 feet. And this angle beta, using law of sines at that point, we can find an angle of 23.8 degrees. So there was enough information before, but now we explicitly have that angle. So that's complete. We know the system's in equilibrium, so we know that for 2D rigid body equilibrium, we're going to have 3 equations that we can get out of it. Now, force equations, if our free body diagram is complete, are going to almost always be very easy to write. The moment, as we'll see in this one, gets a little bit more complicated. So for equation 1, sum of forces x, what is the right-hand side going to be for this one? Right, all of ax. Right, so fk cosine 23.8 degrees. And to reiterate, the pin at A, I'm making the assumption that AX is positive, or is to the right, and AY is up. That could go in either direction. Down here at the spring at B, I'm making the assumption that FK is in tension, and that will reflect how, because it's a spring, we're probably going to need a Hooke's law equation, as we'll see. That means we have to use the Hooke's law under the assumption that tension is positive. All right, so that's our first equation. We have 2 unknowns, 1 equation, so I'll just put it aside for right now. If I write equation 2, sum of forces y. So what is my right-hand side for this? Right, so here we do have the weight in this problem to consider. They're telling us it's a uniform rod, so we can assume that the center of mass is at its geometric center, so 15 pounds down, halfway between. So 15 pounds is that weight that we get out of here. So again, equations 1 and 2, we have 3 unknowns, 2 equations. So because it's a rigid body, we now can take the sum of moments around a point, and that's also going to be equal to 0. So in 2D, we're very often going to have either a pin or a built-in connection that we'll see in the next example. And those are going to be almost always the best place to take the moment about. So again, in this one, we have a pin at A. So algebraically, A is going to do the best. In cases like you see in the homework where there might not be a pin, that's where you might want to consider one point over another. But almost always, the pin is the best place. This equation will be a little bit more complicated than the first two because, again, this involves forces and distances, perpendicular distances. So what is my right-hand side going to be for equation 3? Right, so that's the one piece of it. So remember, back when we were first doing moments, we were always using the perpendicular distance between our force and our point. So if we want the moment around A, for the 15-pound force, this is already completely vertical. The distance we need to use, that is this perpendicular distance between this line of action and the parallel to that line of action that passes through A. So if I extend that up and make it a little bit more obvious, so this hypotenuse here is 1.5 feet. So this distance is going to be the adjacent leg. So 1.5 cosine 30 is that perpendicular distance from the 15 pounds to A. Now 15 is already completely vertical, so we didn't need to split into A components. So it's force times perpendicular distance, and for the 15-pound weight around point A, that's going to cause a positive moment. So positive 15 times 1.5 cosine 30 degrees. Okay, what's another piece of my right-hand side for the moment about A? So this one, I'll try to break it down as much as possible. So you said sine 23.8 degrees. So this is the force part. So what we're going to be doing is for the FK, we do want to break this into its components. So there'll be this vertical component, and this is meant to be horizontal here. And the horizontal component. So by starting with the FK sine 23.8 degrees, that is this piece of it. So its line of action goes here. So right, this is the distance to there. So the force is FK sine 23.8. The distance is this 3. The adjacent to that is 3 cosine 30. So FK sine 23.8 times a distance of 3 cosine 30. Again, that's that D parallel. So we do have two trig terms here, breaking this into vertical, horizontal components and breaking the distance into vertical, horizontal components. And for the vertical component of Fk, that is going to cause a clockwise rotation around A. So right, that's going to be negative. All right, and then one more piece to this. All right, so in this case, the horizontal component of Fk also creates a moment about A. So here, its line of action is getting a little bit cluttered here, but its line of action is this far from point A. So that distance is going to be 3 sine 30, which it's also this distance. So 3 sine 30 is this perpendicular distance. So the horizontal component of Fk, but the vertical component of the rod itself. So again, this is the force times the distance. And this is also going to be negative around point A. Ax and Ay are not in this equation because they have lines of action passing through A. So keep in mind what we wanted to, I didn't rewrite it here, but what we're trying to find in this ultimately is what the spring constant is that keeps this in equilibrium in this position. So if we look at these three equations we wrote, we have three unknowns. So the system is solvable. However, we always want to reflect on what the find was. Ultimately, we need to find that spring constant K. That does not appear in any of the three equations that I wrote up here so far. So it's solvable at this point. So I would say if we're doing it by hand, we probably want to start solving as soon as possible, but we can go back and write more equations. So based on equation 3, because we picked that point A to take the moment about, we can easily find the force in the spring is 8.05 pounds. And because we have equations 1 and 2, we can put that result into 1 and get Ax is 7.36 pounds. And we can put that into equation 2 and get that Ay is 11.8 pounds. It's actually going to turn out we don't need Ax and Ay, but we don't necessarily know that at this point. There's no harm in solving them. It might just be by hand, it's just a little bit more work. And in real life, we probably would be interested in what these pin reactions are. For the problem, though, the only thing we need to find is K, which we'll see when we write our fourth equation, has nothing to do with Ax and Ay. Right, so now we have to come back to the step because we still don't know what K is. So what's our fourth equation, at least in terms of variables? Right, so we can use this formulation of Hooke's law. So again, we're assuming tension. So the force in the spring is the spring constant times the equilibrium length, quantity, equilibrium length minus unstretched length. So we do have numbers for most, at this point we have numbers for Fk is 8.05. K we still don't know. Through law of cosines, we know its current or equilibrium length. And through the givens, we knew it was originally 3 feet long. So solving equation 4, we get that the spring constant for equilibrium has to be 11.2 pounds per foot. Our lengths are both in feet, and our force is in pounds, so it'll be pounds per foot. You have to be careful with English measurements because it could be per inch. These could be kip. So really the same problem can happen in SI units also, but you want to pay particular attention here when you have pounds per foot versus pounds per inch, or newtons per meter versus newtons per millimeter at this step.